Hi, this is Senior Design Group 20 of the Summer 2026 semester. Today we're showcasing FROGS, that stands for Filtration Resource for Off-Grade Systems, which is a fully autonomous reverse osmosis water purification system built for remote and off-grid deployment. The problem we're solving is straightforward. Clean drinking water isn't often available where people need it most. Disaster relief zones, remote field research sites, off-grid communities. Existing solutions either require a stable power grid, constant manual operation, or both. FROGS is designed to remove that dependency. It runs entirely on battery power, makes its own decisions about when it's safe to pump and purify water, and can pull from a source bucket or feed directly from a hose into a water source, like a lake or ocean, depending on how it's deployed. Right now, what we're featuring is the hardware side of the system, the physical components that make it work. We're going to walk through the pumps that move the water, the filtration and testing hardware that keeps it safe, and the power and safety infrastructure that lets it run unattended in the field. Each part you'll see here plays a specific, deliberate role in that chain. I do want to set expectations up front. We're still waiting on a few remaining components before you can move into full system assembly. So what you're seeing today is the first iteration of the hardware, the individual pieces, not yet the complete integrated build. Full assembly and end-to-end testing are to come next. Starting off, we're going to feature our LiFePO4 battery bank. This is what makes the system run off-grid and no external power is required in the field that charges the entire system. Moving on to our bus bars, we have both positive and negative bus bars that form our star ground point, and they're external to the PCBs themselves. This keeps our high current pump return separated from our sensitive logic and sensor grounds, which matters for signal integrity. Next up, we have various mounting hardware for our pumps and our filters. We have a 20 amp circuit breaker that protects the whole power distribution system from overcurrent conditions, which introduces a hard electrical safety requirement. Here's our feed pump, which is named Pump 1 in our system. Its job is to draw water from the source, whether that's a bucket or a direct hose intake, and push it into the filtration stage at low pressure. It's the first thing that activates, and everything downstream depends on it running cleanly first. Our system actually uses two filter stages working together to protect and support the reverse osmosis process. The first is a pre-filter, which catches sediment and other large particles and debris before water ever reaches the membrane. This stage is critical because the RO membrane is the most expensive and fragile component in the system, so the pre-filter exists purely to protect it and extend its service life. The second stage is the RO membrane itself, which is where the actual purification happens. It's a much finer filtration layer that removes dissolved solids, including salts and contaminants at the molecular level, producing the clean, permeate water. Here we have our high pressure pump. We're using the PumpTech 113C, which is our reverse osmosis pump, also known as Pump 2 in our architecture. This is where the actual reverse osmosis happens. It forces water through the membrane at high pressure to separate clean permeate from the concentrated reject stream. It's the highest power draw in our system at 15 amps, which is why it only activates after the low pressure pump has been running for a set threshold and we've confirmed active flow. That interlock prevents the pump from ever running dry. Here we have a needle valve that sits on the housing of our high pressure membrane that lets us tune back the pressure to meet our expected range of about 800 psi, which is then reflected on our pressure gauge. We're actually using two different hose types here, each suited to a different pressure zone in the system. Starting off with this clear hose, which is a vinyl low pressure hose that handles the inlet feed line, pulling water in from the source, and the output lines carrying finished product and reject water away from the system. Since these are only exposed to low pressure flow, vinyl is lightweight, flexible, and more than sufficient for the job. We have a hydraulic hose, which is rated for high pressure and is plumbed between the RO filter and the high pressure pump. It also acts as a dampener, absorbing pressure pulsations from the pump so we don't get pressure spikes or hammering effects that could stress the filter, fittings, or the pump over the top. Next, we're going to demonstrate our external sensors, which sit outside of the enclosure and in direct contact with the water source. We will be using two of these flow sensors, one tracking input flow and one tracking product output flow. Together, they let us calculate the recovery ratio in real time, essentially what percentage of the water going into the membrane comes out as usable product. For our system, we're targeting around 15% water recovery, so these sensors let us verify the membrane is actually hitting that target rather than just assuming it based on pump specs. Here we have a TDS probe, which measures total dissolved solids in the water, essentially telling us how much is dissolved in it and giving us a read on water quality. It connects into a custom PCB we designed specifically for this sensor. We also have a simple mechanical float switch that acts as a safeguard and confirms that there's actually water available at the source before either pump is allowed to activate. No water, no pump activation. It's an interlock against dry run damage. The sensor here on the far right is our DS18B20 temperature sensor, measuring water temperature at the source. Its main role is supporting the TDS probe. TDS is really a conductivity measurement, and conductivity shifts with temperature. Warmer water reads falsely high in dissolved solids, even with no added contamination. So we feed this reading into our TDS conversion to compensate for that, keeping our readings accurate across variable field conditions. Now we're moving on to our internal components, the custom PCBs we designed in-house, starting with our 3.3 volt LM2596 regulator, which is tested and working. It provides regulated logic power to our ESP32 and sensor. Moving on to our pump switches, we are using a BTS 7002 high side switch. We have two of them built, here and here. They have both been tested individually and work. They handle high side switching for our pumps, letting the system turn them on and off under software control while protecting against fault conditions. We also have our TDS board, as mentioned earlier, which is our custom PCB that our probe connects into. Right now, we have 2 out of the 3 of these peripheral boards fully met and confirmed working. As you can see, we've implemented this on a breadboard for now, since we're still waiting on our MCU board to be fully populated. Our MCU board is our final piece. It's fully prepared, but we ordered the wrong pin package for our CP2102N, our USB to UART programming chip. Their correct package has already been ordered and is on its way. Once that arrives and we get the motherboard put together, we expect to be finished with the internal hardware side entirely and ready to move into full system assembly. Right here, we are showing off our LM2596 3.3 volt fixed regulator. Up top, we have a 12 volt input and we have a 3.26 output voltage.